All right, so we're excited to kick off our panel on future autonomous urban air mobility. Joining me on the panel is Dr. Eric Muir, founder and CEO of Volair. So we also have Stephen Crouch, co-founder of Volair. So welcome again.
So Eric Muir, I have a background in aerospace engineering, studied at the University of Michigan, really got introduced to the problem we're going to discuss today as an engineer and a leader at Boeing, where we were pioneering some new technologies that were really focused on, eventual automation and autonomy for aircraft, but really just filling out the whole technology stack around sensing and perceiving the environment. So that kind of led me after a shorter stint with a cloud startup called Rescale to join Stephen here in founding Volair.
Yeah, and I'm Stephen Crouch. My background's in physics, particularly radar and LiDAR sensor physics. I co-founded a company called Blackmore, which was acquired by Aurora Innovation a few years ago. And so that kind of brought me into the autonomous vehicle space. And so I'm coming to this UAM problem really from that perspective of autonomous vehicles.
So again, I think the question that I have posed for both of you is the problem statement in terms of, I think the areas that you guys are trying to address is the limitation of the current aviation ecosystem, as well as the shortage of existing infrastructure, and as well as the experienced pilots. So if you could elaborate on that, that'd be great.
Yeah, absolutely. Yeah, I mean, it's an exciting time in aviation and aerospace. We see headlines every day about new aircraft designs, largely being fueled by new battery technology, electric propulsion. But to accompany all those headlines, you also see challenges even with existing airline operations, where there's challenges with pilot shortages. Obviously, COVID changed a lot of demographics in terms of where people are living. It's putting pressures on, different airports that exist. And so if you kind of look forward into this landscape, you see a few different challenges and early opportunities where technology can help. The first one being with the increasing demand and application of aerial vehicles, whether it's for moving people or moving goods, where are the pilots going to come from? We've benefited in past from the military being a large feeder of well-trained aircraft that go into the commercial aviation sector, and also we've just come to the reality that becoming a pilot is a very skilled trade. It takes a lot of training, 1,500 hours of different flight hours. So when you couple that also with this problem that the existing aviation infrastructure has largely centered around this hub and spoke model with a few, talking tens of airports in the country that have a lot of the infrastructure needed to fly these aircraft in all weather conditions and support the volume of traffic that is being projected. You kind of have a double-edged sword there with two different challenges, pilot shortage and also aviation infrastructure. So that gives us an opportunity to look at the advances in the autonomous vehicle space, the sensing space, software, and other technologies that can help this problem by providing additional situational awareness to help maybe pilots that are, have lower time, or maybe transition into different aircraft or different operational modes, and then eventually mature those technologies to be able to enable this kind of larger scale of aircraft and operations to leverage the tens of thousands of airports we have throughout the country and move people and goods point to point where they need to be, when they need to be, without some of the constraints of the existing system.
So what is Volair, and how is Volair trying to address some of these issues and limitations?
Yeah, so kind of at the core of what Eric is talking about there is just a huge variety of different applications in terms of commercial vehicles or aviation, general aviation, automated aviation. And so across the board there's a need for, different sensors, different technology to solve some of these issues. And in each of those cases, there's really a lack of tools in terms of how to consume that technology to come to some of the the points that these different applications want to make. So we're looking at developing combinations of software and hardware. So kind of an end-to-end stack that's both very simulatable to kind of take advantage of some of the cost savings of simulation, but that also really translates into the real world. Whether it's things like landing hazard assessment for like an eVTOL coming into a location to land, whether it's automation of like ground operations for a commercial jetliner. Those actually have some kind of commonalities that we can start to highlight in the software and sensors that we're looking at. And I think when we start looking at providing common tools and common solutions, that's going to have a better chance of being successful when you look at the uncertainty of timing around when some of these things are going to be ready to kind of for prime time in these different kind of application lanes within aviation.
So if you could talk a little bit about the different types of customer segments and how you would support them from a hardware and software, essentially kind of this OS surround sound for each of those segments.
Yeah, sure. So, if you look at the aviation industry, you have general aviation aircraft, small, 4-6-seater aircraft. But those aircraft are actually increasing in demand and increasing platform for automation and safety. People want to be able to fly for business or fly their families safely. And as you progress through that, there's smaller cargo operations for flying our Amazon Prime deliveries around and what have you that are oftentimes flying kind of mid-range size aircraft, fixed wing. And then staying on the fixed wing track, you get into larger commercial aviation that we're all very familiar with flying around the country. In that case, it's obviously different. There's people on board and very high safety record, but you have 2 pilots and a lot of logistics in terms of flight crew scheduling and things of that nature. And so as you kind of go through that particular lane of fixed wing aircraft, and those are existing operations today. There's an opportunity to provide sensing and decision-making type and just situational awareness type technologies, both on the software as well as using hardware to also do that, much like pilot would use their eyes and other resources to just continue to improve the safety of those operations at airports that maybe don't have a control tower to help with traffic awareness. Maybe they don't have an automated landing system infrastructure in place to help aircraft get onto the ground in lower visibility conditions. So that kind of is, what we see in the existing market. But then you also look at all the excitement around, urban air mobility, electric propulsion aircraft that are going to be flying in urban environments. They have a different mode of operation in that they take off and land vertically a lot of times, or maybe there's an e-stall concept that has a short takeoff and landing. But a common aspect to those is they are all, there's an anticipation that the real benefit of those aircraft is the ability to operate in and out of vertiports or other, kind of airport environments that don't exist today. And so as you talk about, where are we going to build these new vertiports or short urban airports, comes the question also, well, what other technologies need to be put into that infrastructure to match the same type of operational capability you might have at LaGuardia or SeaTac or something of that nature. And it's obviously a challenge. And so if you can bring to those new vehicles as they're being developed, software and hardware technologies onto the aircraft to bring a lot of capability that a well-trained human pilot could bring to the scenario, provides a lot of value there. And then, can also help with just the pilot shortage challenge I talked about, as we look into the future as well.
Yeah, in terms of the customer set as well, Scott, we're looking at everything from like startups in the eVTOL space to kind of like tier 1 avionics providers, all the way up through like the big commercial, aircraft manufacturers. In a lot of cases, we're finding R&D teams or kind of early stage development teams that have a mandate to really bring this technology to market and start to kind of make these upgrades available within these different segments. And, a lot of these guys are just stuck kind of starting from scratch with the tools around, how do I get data off of some camera, or how do I deal with this new LiDAR sensor, or what sensor should I even be thinking about using for these various applications? And, there's a big concern when you look at the variety of kind of functions that need to be addressed to meet some of these challenges, that you might turn your airplane into kind of a Christmas tree covered in sensors. And so one thing we're trying to do is kind of really focus on, okay, these are like the 2 or 3 sensors you need that are going to get the most mileage. And here's kind of the end-to-end concept about, how those really fit into those functions.
Yeah, so both of you have covered quite a bit. So let me just kind of review a little bit quickly, is that when we think about the gradient of autonomy from, let's say, level 1 all the way to level 5, is that you can support advancements and safety, kind of similar to, ADAS in cars, as we are very familiar with, to eventually all the way to, level 3, level 4 plus autonomy. And moreover, I think one of the things that you've also communicated is it's the system and the hardware that's within these vehicles, but also it's the platform by which the operators, let's say the regionals or the vertiports, that are also utilizing as well. So it's this common platform that works across the different players so that there is a common communication and orchestration, right? And then the last piece that I heard was this notion of best practices and really consulting aspects around, as these different players and manufacturers and segments start to think about automating some of these things, what are some of the things that they should be thinking about, but more importantly, the toolkits as well as the best practices that you would support. Is that correct?
Yeah, I think that's a great kind of concise summary.
We should, well, I guess we are recording this. It's perfect.
All right. Now I have to say, listening to that, it does feel a lot. So I wonder if you could talk about kind of the core of your IP that differentiates you guys from somebody else, maybe that are coming from autonomy. Maybe it was more ground-based, but they could, port it over to urban air mobility. So what is it that you guys do well? And I think it was around simulation and modeling. So if you could talk more about that.
Yeah, sure. No, you're right. I mean, when you look at autonomous vehicles in general, whether they're ground or in the air, there's an enormous kind of ecosystem of technology that needs to be put in place. And so where we're focusing is kind of actually like in three pillars, if you will, sensing and simulation, and then kind of the whole data aspect of how you develop some modern technologies surrounding say sensing and perceiving of the environment. And those 3 pillars can kind of core up to provide an autonomous, flight solution with, perceptive as well as like future state prediction type capabilities. So, I think probably the 2 main that are the most interesting to talk about are on the sensing and the simulation side. And that's where you kind of tie together the hardware and software components that Stephen was mentioning. So on the sensing side, it's understanding that the various modalities of sensors available, and also understanding that the different problems that are unique to aviation that need to be solved. We understand for ground vehicles, when are cameras most valuable, when are radar, when are LiDAR. Those types of sensors are still worth consideration, but the types of problems you're trying to solve are very different. Aircraft fly in visible moisture or above clouds and things like that. That obviously obscures the value, say, of camera. So there's kind of that aspect of just the hardware piece. But then the simulation, I'll let Stephen kind of expand on this more as well. But the simulation really is a core aspect of not only just kind of this early assessment of the sensors, but also the ability to study the entire flight envelope or kind of the entire design space of that aircraft and the operation of that sensor, so that you can, provide the artifacts necessary to, harden a solution, let's say for a landing hazard assessment, making sure there's no aircraft in the landing zone prior to, to touchdown. You can't simulate you can't, test every situation. Testing in aerospace is an order of magnitude more expensive and more complicated than testing the ground vehicles. And so the simulation is key there as well.
Yeah. So, if you think about like the autonomous vehicle space, there's kind of this, I think, misconception in aviation that there's just this zoo of all these great sensors that you can go source and put on an aircraft and solve your problems very quickly, and that may be true in some cases. But one thing that simulation is going to allow is kind of a more direct understanding of what's possible with some of these new technologies that are coming out within autonomous vehicles. it's going to allow a much faster look at really how they might perform. I'm thinking about things like range, field of view. I mean, fairly basic, kind of concepts of kind of sensor performance. But in having a look at that through simulation, it's going to allow, from the perspective of automotive, some fairly small players from a market size perspective to really kind of get to the point and have some better conversations with some of these sensor providers so that, they're not wasting time iterating 5 times through what they think might be some great product for, an electric aircraft, kind of like landing application, for example. It's going to be much more effective if they're coming to the table, having really done their homework within simulation, and they're asking for the thing that they actually need, versus, kind of hoping that they're going to capture the interest of, quite frankly, companies that are looking at just much larger volumes in the automotive sector at this point.
So let me go back to sensing first. If you could talk about specific to flight, aerial vehicles, what are the kind of sensors that are more appropriate given the fact that, like you said, you have these water moistures and clouds and things that really obscure the view of typical cameras?
Yeah. I mean, that's just like obviously just straight up like a problem. If you're going to have clouds or like you said, some kind of, foggy scenarios, especially in an urban environment, that's going to be really difficult to rely on that. And another big aspect of the use of cameras, we think, is the requirement really of looking at some pretty heavy compute hardware to make effective use of that data. It may be possible at some point to certify like a neural network for certain applications, but that becomes much more of a black box from the FAA's perspective than like a really direct 3D image that's derived from maybe LiDAR or radar. And so when we think about this, it kind of starts to look like there's going to be more of an over-indexing on sensor quality with an effort to make the actual inferencing and use of that data a little bit more straightforward and a little bit more explainable to the FAA than what we see currently, where there's just black boxes all over the place within an autonomous vehicle kind of perception stack.
So you bring up a really good point, which is to be FAA certified as a software or hardware, you have to go through this process. And part of that is the FAA being able to actually see what's the data, what is it actually relying on, and how is it actually making those decisions. So to that point, staying with, let's say, LiDARs and radars, for instance, talk to us about how are you capturing that data and then feeding it to the actual simulation models to come up with these different common cases.
Yeah, so there's really a variety of things that need to be pulled in. Everything from really the geometry of a scene over to really some of the fundamental kind of features or specifications of part of a sensor that you need to kind of aggregate into a realistic simulation. And then you're kind of asking about some of our core IP, Scott. It's really about how you close that loop between the simulation and what's being produced in terms of data, and then how you actually validate that. If you go capture some real data with a sensor that you've modeled and show that, hey, our simulated data actually looks pretty much like the real stuff. And that's kind of a loop that I think Eric could talk about within just the FAA certifying a jet engine. They like to see very similar things where somebody's gone through the steps with their fluid dynamic simulations or whatever, and shown this is what we expect to happen. And then they go run a few real world tests and show that that's actually the case. And so being able to kind of close that gap is going to be very important when it comes to simulation, kind of, ultimately providing the cost savings that it can.
Yeah, and I was just going to add too. I think a key aspect that pulls from the analogy from certification of other systems on an aircraft that have been jet engines, aerodynamic structures that have been around for a long time is this kind of physics based principles of your simulation. Is that you're relying on the actual physics and geometry of the world that you're simulating to be able to, to explore these edge conditions and really a larger design space than is feasible to do in testing. But when you do that physical test and you're able to compare the data, if there's some adjustments, but there's a physical understanding as to, if they correlate well or not and why. It's not just, a simulated image that, hey, that looks pretty good this time, but the next time something spits out, you're like, like the dog has two heads, it doesn't make sense, so it's a little more physics-based and realistic.
Yeah, I think that's a great point. And oftentimes, of course, these modeling systems that you're using, of course, embodies a lot of these physical algorithms that you're referring to. So talk to us about, how you guys are potentially working with partners, potential new customers, capturing new data from these different modalities, and then feeding into your different models for exactly what you're talking about.
Yeah, sure. So, the kind of the first step is, we're developing these simulation models, and we're doing our own internal, validation of making sure we've got the right physics, we've got the right information built in, and closing that loop, like Stephen mentioned, internally. And then, when we start then bringing in partners or other co-collaborators and things like that, it allows us to take that kind of a flexible tool chain and study a particular problem, landing hazard assessment or navigation for approach to landing at a remote airport or something like that. And so if they have a different vehicle, has different dynamics, maybe they've spec'd out a sensor from a different supplier than we've, previously tested ourselves. It allows us to apply this, more flexible simulation tool chain to their problem, or really be ahead of them even specking out those sensors is kind of the ideal, and working with them through, kind of the down selection of sensors. If there's flight testing that needs to be done, simulation, and kind of closing the loop with them.
Well, one thing you might find interesting, kind of as a follow-on to that, Scott, is, when it comes to, aviation, a lot of times the perspective is from the sky down, like looking at the world. And that perspective is really shared by a huge amount of kind of different geospatial data resources, whether it's LiDAR surveys or like synthetic aperture radar data for DEMs or satellite imagery. A lot of these things are available as kind of a really good substrate to build simulations off of. And that's a little bit different than kind of the autonomous vehicle world, or just the automotive world, where you kind of have to go and get at ground level regularly to kind of get all that data built up. So that's a head start, with this kind of shared perspective of really just the overhead view that we're trying to take advantage of within these simulations as well, so that anything we do should very quickly apply to like different locations, say, at least around the United States, if not globally.
Yeah, I think, Stephen, the last comment that you made is actually very important, and that's a key distinction for those that are not super familiar in the aerial space that you're talking about. So I think that's right on. Both of you have talked about this, which is the distinctive value add, but the competitive advantage that Volair has is this notion of supporting design, production, and really even the Q&A process, not in actual physical flight, but doing a lot of that in simulation, using the physics, using the dynamics of how the physical world works, using exactly the macro types of data that you're talking about from an aerial perspective, and that has incredible value from a time to market, as well as really the fidelity and the rigor and the trustworthiness, if that makes sense, from the data. Is that right?
Yeah, that's right. I mean, I think, as I mentioned, there's just like an enormous energy with new aircrafts that are being developed. And a lot of them are just getting off the paper and into prototypes as we speak. And hundreds and thousands of engineering simulation hours have already gone into those from a vehicle design standpoint. And so, we kind of see an opportunity to work with those manufacturers of these new aircraft, as well as existing, to study the problem in advance of, making some final decisions around, what does this aircraft need to have in 5 years to support some of these new technologies that we're going to onboard, and get into that simulation environment that they're already using for the vehicle design, to be able to kind kind of de-risk, if you will, kind of burn down some technical debt there, and make wise decisions that will benefit them in the future. And maybe an analogy is like what you see with, with Tesla. I mean, they rolled out some of the early, early aspects of their autonomy stack very early on to get it out into the field and start learning about it, so that it can be onboarded with additional capabilities down the road. And I think, you'll see that in aircraft too. Aircraft don't have a 5-year lifespan. They ideally have a 15 or 20-year lifespan. So you need to think ahead as well. And simulation can help with a lot of that right out of the gate.
Excellent. All right. So the last question we have for you is, where are you as a startup in terms of product development, partnerships, customers, funding, as well as just any other projects or things that you want to share?
Yeah, we're fairly early stage. We've been at this for about a year, working with a variety of customers, both within aviation and actually a few outside of aviation, just to kind of get things up and running as a company. That's actually allowed us to kind of delay fundraising a little bit, and really focus on some company building out of the gates. And I think we're really happy with that approach thus far. At this point, we'll be looking in Q1 probably to start a fundraise to start to accelerate some of these activities, and that should align pretty well with some interest that we have from a handful of different potential customers or kind of early collaborators. That really want access to at least some form of kind of these simulation products that we have put together thus far. So yeah, things are going really well, and we're excited about the future of all this.
So I want to thank Dr. Muir and Stephen for a terrific conversation on the future of autonomous UAM. Please give them a round of applause. And we now transition to our quantum computing track.